Hello and welcome back to Calculus 3, section 11.5, Lines and Curves in Space. So, line is a one-dimensional object, like concept, whatever. The line can be oblique in 3D space, could be straight, linear line, could be curved line. And we need to figure out the way to describe the line in space. For instance, you might want to study a mountain road, right? Or you might want to study a piece of rope or a cord of some kind. Well, if you have a cord, right, and you want to study it, meaning the only thing you can figure out here is the length, right? You stretch it and you put it against the measuring tape and you know its length. So having something that you can stretch and measure, it's not a problem. What are you going to do with a mountain road that you can't pick up and stretch and measure, right? So, yeah, exactly. So there are many applications, right, looking at the path of the particle if you are doing particle physics, and many applications of where this would come in handy and useful. So in order for us to sort out all of these lines in space, we are going to use the vector-valued function. So vector-valued function is going to be collection of functions, which is actually parametrization from your chapter 10 from Calc 2. Hi, everyone. Right? Calc 2? Yeah. So chapter 10. Now, if you are a visiting student, meaning you did not take Calculus 2 at RVCC, you might not have the knowledge of parametrization, which is what we cover in chapter 10. Your textbook, the same textbook that is uploaded in my MATLAB, and I see that 25 of you have the account, which means everyone. Chapter 10 is there. Practice problems under the study plan are there. And parametrization is going to play one of the key roles in actually 3 chapters of Calculus 3. So if you don't know it, you are technically doomed. I will go through the subtleties of parametrization, obviously, and explain as much as possible, but you really need to go back, if you haven't had lecture on parametrization, and learn from chapter 10. Whatever book you have, you will find parametrization in the index and go to those pages and learn it there. When I learned Calculus 1, 2, and 3, I learned about parametrization in Calculus 3. But today's curriculum that we are running here at RV has the parametrization in Calc 2, and I understand that many other schools do not have that in Calc 2. So pay attention to that. Now, the vector-valued function is a collection of functions in a vector. So we are going to say R of t, that's the notation instead of f of x. Now you have R of t, and that's going to be the vector of 3 functions. In this case, x of t, y of t, and z of t. It can be any dimension, guys. It could be 2 functions for 2D space, 3 functions for 3D, 7 functions for 7D, and so on. So we have the notion of a vector-valued function, and that is simply a collection of functions, and these functions are parametric functions that we study in chapter 10. Now, before I continue, I'm going to briefly go over parametrization and parametric functions so you know what is happening here. And then, ask if you have more questions. Clearly, stop by office hours and then read the book. I mean, paid money for it. So, first off, what parametrization does is it reduces a parameter t, or theta, or whatever you pick, as an extra variable, but it's not a variable, it's a parameter, and breaks the dimensions of the original equation you have in number of equations. So, if I have, let's say, y equals x squared minus 1, right? If I have this, this is clearly a 2D equation. It has coordinate, right, x, y ordered pair. Now, what I can do is I can introduce parameter t and cast this, say, x equals t, in which case y equals t squared minus 1. This is known as parametric pair. Observe that both x dimension and y dimension depend on the same parameter t, and you can treat that t as time. So now you can observe evolution of dimension x and dimension y in respect to time, rather than having dimensions x and a y together in one equation. Now you would say, well, why, right? Well, give me a second, okay? Because the next example will address that question. Right now, let's just have this completely pointless example that outlines just the procedure, okay? And the meaning of the thing. But yes, this is pointless because no one will ever parametricize that, because you don't have to, right? Exactly. So exactly that. So what can I do now? Instead of assigning x's and computing y's, I can assign time. Time 0, time 1, time 2, time 3. Say seconds or years or whatever. And then we can use our equations to compute x and y. So, because x is equal to t, x's will be 0, 1, 2, and 3. And y will be calculated in the y equation as t is 0 and so on. So we have what? Negative 1, 0, 3, and 8. Which creates ordered pairs 0, negative 1, 1, 0, 2, 3, and 3, 8. So when you are looking at these, right, you say, all right, now I have ordered pairs, I can plot this, and I can get the graph. Well, you are going to get the parabola graph. You are going to get the graph that you would get with this, right? So this example was just, a quick example for you to just hopefully get the understanding that we are completely, with these parametric equations, separating dimension x from dimension y into two separate equations, and have one equation explain progression of dimension x in terms of, let's say, time, and then the other one progression of dimension y in, again, in respect to time. But now let's take a look at a much better example that makes much more sense to parametricize, and that would be equation of the circle. So if I have x squared plus y squared equals to 16, this is a circle with radius 4, thank you.
4.
Yes. So circle with radius 4. Now, if you observe the circle with radius 4, you see it's not a function. Calculus is performed on functions. So yes, there is implicit differentiation, so you can, deal with that and differentiate. For integrals, you really have to go and pull off some magic to do this, right? Because it's going to be trig substitution at best. So, exactly. So now what I can do here is, instead of having my x and y dimensions on the pile, I'm going to separate this into two parametric equations. One is going to be x equals 4 cosine theta, and the other one is y equal 4 sine theta. And these equations now create a parametric set that describes the same equation up there. Why have I done this? Well, for the most obvious reason here is that circle is not a function. Both of these functions are functions, right? Function is a function, right? So we took something that it's not a function and we parametricized it in a way where we got two functions. I have each of the dimensions represented by an equation which is a function. Now I can do a lot of stuff with functions, and I can't do too many things with equations that are not functions. So that's one of the clear benefits. Another thing is that parametrization, since it's introducing one more variable, well, parameter, it's going to introduce another, what we call degree of freedom. So we get something else for free. And in this case, it would be the direction of motion along the line. If you are using this parametrization, direction of motion is going to be counterclockwise along the circle. And for parabola, which I didn't get to draw, I'll try to squeeze it over here. For parabola, with parametric equation, we also have to add these arrows showing the progression, because the time flows in one direction as far as we know it, which is from 0 to 1 to 2 to 3. That type of a progression will clearly outline which point, right, is first and which one is second and which one is third, right, in the progression of motion. Now I can swap the orientation of motion by simply interchanging sine and cosine and leaving x and y where they are. So if I have x in terms of sine and y in terms of cosine, that would switch the rotation and progression into clockwise progression. This will be used later in class in chapter 14, because we will be dealing with line integrals, and line integrals will be done over parametricized equations. So your entire chapter 14 depends on this, and if you can't parametricize, well, yeah, it's a quarter of your course gone. So you have to be, you have to talk to me if you've never seen this before, and if you are not comfortable. So office hours, and also a whole bunch of YouTube videos, and the book has, right, chapter 10 for you to practice these things. We just know it. Also for the ellipse, right? So if these guys, 4 and 4, if those are the same numbers, it's a circle. But if it's 2 and 5, it's an ellipse, right? So we have we just know what they are, right? Now you can the exercise when I teach this well, actually on my channel. You guys can find the videos. If you type my name in YouTube, right, all of these videos that I'm casting now are on my channel. You can find for Calculus 2, look for Calculus 2 10.1 video, and that's parametrization. 10.2 will be polar coordinates, and 10.3 would be calculus in polar coordinates. Those 3 videos you need to know in order to survive chapters 13 and 14. And I mean, if you are visiting students, if you're RVCC student, like some of you are, then you better know this stuff, otherwise doom. Yeah. All right. So now we are going to take a look at this parametric set over here. And I'm going to just now put this in the vector like this. So parametric set, good old stuff from chapter 10, from Calc 2 in this case, is now going to be placed into this. Now, we don't care whether the parameter is S or T or theta, whatever letter you use, right, other than X, Y, Z, because you are parametricizing those. We are going to use T for time, S for arc length parameterization, and theta for angle, if something depends on angle, like right sines and cosines, circles, and so on. So those are the parameters that we are going to use. So what is a vector-valued function? Vector-valued function is going to be a collection of these parametric equations that describe some kind of curve in space. If you have only two equations inside, it's a two-dimensional vector-valued function, and it describes a curve in 2D. So that's a piece of chalk, and you draw on the floor, right? That's all it is. So you have your sine curve, you have your circle, you have your ln x or x squared, whatever you want to have. All of those can be parametricized and placed into this. If you have three functions inside the vector-valued function, that means that the space that you are the curve that you are parametricizing is a three-dimensional curve, and you can think of the, well, I'm going to write the equation of the spring, right? That equation is actually called a helix, and some of you know what the helix is, right? So any curve in 3D will have representation in parametric, we'll have parametric representation, and we will call those, right, vector-valued functions. Now, vector-valued function, let me go now and just give another example. Actually, this line, you know what, I'm going to move this. There you go. Yeah, do this in your notebook. Now, what I'm going to do is I'm going to give an example of RT is equal to, say, t squared, t minus 1, and square root of t, whatever. All right? So this is an example of the vector-valued function in 3 dimensions. What this looks like in 3D, I have no clue. I just put whatever on a paper because, yeah, we can do that. Now, you actually can go into Mathematica, which is installed on these computers and hopefully on your computers as well, what I give you the thing, and plug that in and graph it.
You put it in the 40 brackets?
Not as obvious, so yeah. We'll have to see it later. So now, what do I want to, what do you guys need to understand? You need to understand that for every timestamp, or whatever, right, at t equals to 0, you get a vector. So if I'm calculating r at time 0, the vector is 0, negative 1, 0. If I'm calculating time at 1, it is 1, 0, 1. If I'm calculating time at, 2, yeah, it should be 4 because of square root, but, all right, 2 is going to be 4, 1, and root 2. Not that great, right? Let's go r at 4 because that's the easy one. R at 4 is going to be 16, 3, 2. You see that I'm getting vectors, right? These vectors have the terminal point. And when you connect the space curve through those terminal points of vectors, you are getting the space curve that this vector represents. Remember how you can always come up with a table of values. Let's say you don't know what the graph looks like for a particular function, y equal f of x. What are you going to do? you're going to create table of values, pick 0, 1, 2, 3, 4, 5 for x, compute y's, plot those points, and connect the dots. Just like in a coloring book, right? You don't have to color them. We are doing the same thing here. You are calculating at 0, calculating at 1, at 2, at 3, at 4, at 5, and whatever, and you get vectors. You plot those vectors in a 3D space, and the tips of those vectors are where the points are through which the curve goes. So, a quick representation without us actually going and drawing all of these precisely or whatever. The space curve that we get, which we label as R of t, is going to have these vectors pointing right to the right. So this might be t equals 0, t equal 1, t equal 2, t equal 3, and t equal to 4. So now you have this space curve whose each point is described by the vector, and all of those vectors actually are generated from the vector valued function. So computing values in vector valued functions is the same as computing values in your f of x function, except you have 3 calculations instead of 1, right? Because you have to do calculation for x and calculation for y and calculation for z.
So when we go to like integrate them, we just do
Yes.
piece.
And that's the greatest part about all of this. So you are technically going to take the limit and differentiate and integrate vector valued function to obtain the acceleration and the position of the particle and the velocity of the particle, right, which moves along that path.
Yeah.
And you will do those integrals component-wise. So you don't care if the particle is moving inside a circle, which you can't integrate easily, right? But through the parametric equations, not a problem. Because each one, as you can see, are very easy functions to integrate, even if they are sines and cosines. Before we jump into calculus of these things, let's talk about linear line, the straight line in 3D space. We already know that axes are lines, right? So those go along the ijk vectors. But what about any other line, right? So if I want to draw easy lines, I will just draw on the wall, on the ceiling, on the board. But what about this line, right? Which in relation to our XYZ coordinate system that is set in a corner over there is not really parallel to any of the planes that we call basic planes, right? What is the equation of this particular line? So let's derive equation for the lines in space. So we are talking about linear line in R3 in 3D. R3. Exactly. So we are going to start with the coordinate system. And the knowledge that we need to have is that any straight linear line, right? Linear line or straight line is completely determined by 2 points. To suspend a rope, you need to tie it on 2 ends, right? Cable, power cables, phone cables, TV cables, right? All of those are suspended at 2 points. So to define a straight line, the least amount of points that you can have is 2. If you have only 1 point in space, then the line is going to wobble and rotate around that point. If I have 2 points, well, that fixes it. I can't really move this in any other way because you will lose the connection with one of the points. So you must have 2 points to describe the line. So I'm going to put line with 2 points which define that line. And those could be any 2 points on that line. It doesn't matter which ones.
So then we need the length, just telling you where it is.
Exactly. Line is infinite in length, right? It extends infinitely in all directions. So we have a line in space, which is here, infinite, right, in both directions. And we have 2 points which describe that line. Now what I'm going to do is I'm going to stretch 2 vectors from origin to each of these points.
So, is this not like position vector from status class?
Yes, it is. So now what we are going to do is we are going to call this point here, point P0, with coordinates x0, y0, z0. And we can call this, if you want to call this fixed point, you can call it fixed point. And this red vector here on the left, the red vector is going to be called R0 vector. Which is x0, y0, z0, right? Because that's the terminal point that it hits. On the other side, I'm going to have a point P, x, y, z, and its corresponding vector R, which is going to have coordinates x, y, z. Great. Now, I also need to call attention over here to the vector which stretches between these 2 points. And I'm going to call that vector v. You see, that vector v carries this third-dimensional slope, the steepness of the line. And we will call that vector v. That vector v is going to have the components a, b, c. So I'm going to put in quotes over here 3D slope. That vector v is 3D slope. The way the line tilts, or I'm not going to say curve, the way the line tilts in 3D, right? The orientation on the line. So that v is obviously extremely important. So what do I have at the end?
A bunch of vectors.
I have a bunch of vectors. But do you guys see the addition of vectors where you have that the vector r is the vector r0 plus the vector v, and we need to multiply that by the parameter t. So I have to put in a t over here as well, because there's progression in time to get from point P0 to the point P. So it's direction times time to get there. So what do you know from your previous life? You know that y equals mx plus b, right? It's the same thing. Now, you are going to have r is equal to vt plus r0. It's the same thing. It has to be. It's a line. This works for 4D and 5D. If you want to have a straight line in 17-dimensional space, this is the equation for it. This equation over here doesn't depend on the dimension, because the amount of variables within RV and R0 will determine the dimensionality of your problem. So, since I want this to be defined for 3D, I'm going to say that my vector R is vector xyz, vector v, previously defined as abc, times t, plus vector r0, which is x0, y0, z0. Guys, that's the point that it's given. You know that there's going to be a problem. Write the equation of the line that goes through point 307. That's 307, right? 307 is x0, y0, z0. That is the fixed point that you have, and you want to shoot your line through that point. So now, I call this the exploded view of this equation. And since we are in 3D, each vector has 3 components. Now, generalize this to any dimension you want. You can, all right? So now, I am going to separate 3 equations, right, in a parametric fashion, and say that x is equal to at plus x0, y is equal to bt plus y0, and z is equal to ct plus z0. These 3 together create a 3D equation of the line. So these work together. You can't pick one of them. Together, they describe the line in 3D space. So this over here, all of this, is line in R3. Let's see. Find the equation of the line through, I said 307 and 912, whatever. I am giving you 2 points in space, and I'm asking you to find the equation of the line. All right. The way to do this is to first say, this is my 307, which is my x0, y0, z0. And I also have another point, 912. I need 912 so that I can get my vector v. Remember that you have to have 2 points to find the slope. To find the slope in algebra, it was y2 minus y1 over x2 minus x1. Now, you find the slope by simply subtracting these 2 points, because all you need is the vector that stretches between them, and that's the vector v. So vector v is going to be 9 minus 3, comma, 1 minus 0, comma, 2 minus 7. It's the terminal point, right, minus initial point. So vector v, which is our 3D slope, is 6, 1, negative 5. And All I need to do now is to plug this in the formula and we're done. Our formula is x equals at plus x0. Hey, I have my a and I have my x0. Just plug them in. Y equals bt plus y0. And z equals ct plus z0. This gives us x equals a is 6, so 6t plus 3. Y equals b is 1, so we just have t plus 0. And z equals negative 5t plus 7. This is parametric set. So this is the answer. Another way to represent the solution would be to put all of these in the vector function, which is 6t plus 3, comma, t, comma, negative 5t plus 7. One equation for x, one equation for y, and one equation for z. And as you can see, all of these guys here are linear, which screams this is a linear function. I know them all. So, hint. Yeah. What happened?
So like when we move on to dynamics, we use this to find the acceleration and everything.
Yeah, dynamics is going to take your statics and then take the derivative of it.
Okay.
So yeah, good luck.
What about static?
2 derivatives of it too. That was at one point in time voted as the most notorious course of all courses. Yeah.
Yeah, I got statics and dynamics.
And how are you proposing to do that? Oh, okay. Then fine.
A little better.
What else is going to be very important for chapter 14? Line segments. See, line that we have up there is the line that is going to go infinitely, right? It stretches infinitely. I am not placing any restrictions on t. And because I am not posing any restrictions on t, then the line goes forever. A standard question within much larger question in chapter 14 would be calculate line integral blah 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 along the line segment, and they say line segment between 0, 0, 0 and 5, 5, 5. This is fine. By popular demand, 666. So now, what you have is the line segment that stretches from the origin to the point 666. And we know how to parametricize this. This is my x0, y0, z0 starting point. When I subtract these two, we are going to get our vector v, which is now 666. Actually, 555 and 111 are actual problems, which I worked out with my students 3 weeks ago in Calculus 3, at the end of the previous semester. So 00 to 111 and 00 to 555. So now I have my ABC, I have my x0, y0, z0, So I can quickly come up with 60, 60, and 60 as my parametrization. But now, what is the meaning? And let me actually color code this. So let's use green for the word segment. Line has to start at 0, 0, 0 and stop at 6, 6, 6. It has to start at 0, 0 and stop. Now, this never stops the way it's written. So we need to bound t. And we achieve that by simply saying that in this particular case, t has to be between 0 and 1. Now try it. The lowest value that t is allowed to take is 0 times 0 seconds. So plug in 0, and what is the vector you get? 0, 0, 0, which corresponds to your first point, 0, 0, 0. When t is equal to 1, you get 6, 6, 6, which is the terminal point of the line segment. So now, if you just write this, it's the infinite line. But if you write this and the bound on t, it becomes line segment. Now, for chapter 14, you must have line segments, because you will be computing integral over a finite line. Clearly, that integral computed over the infinite line should be infinite. Right? Well, not always, but yeah, we'll have to expand on that when we'll cross that bridge when we get there. So I have 60, 60, and 60. All right, very good. Pushing forward curves in space. We are going to focus on R3 again. The story goes, any dimension is fine. We already understood from the previous part that your vector valued function r of t is going to be determined by these vectors, because it is a vector valued function. And these calculations happen at t0, t1, t2, t3, equal to 4, and so on. My vector valued function r of t is going to be the collection of f of t, g of t, and h of t for 3D case. So this is my equation, and it's again vector valued function. Now the example of this is the one that I had before, right here. So I might just cut and paste this and place it down there, which I'm not. I'm going to work on the new example, but that's technically what is happening. We also need to know that there is orientation, because your space is 3D space is perfectly defined by x, y, and z, which are the three things you have inside. But then you also have t as the fourth right? By the way, time-space, or I mean space-time, right? What's space-time? X, Y, Z, and T. It's just 4 variables on a pile, right? So now I can observe evolution of the dimension X in respect to time, evolution of Y, and evolution of Z separately, because I have them in a vector-valued function. Now, given that we have 3-dimensional space, but we have 4 variables, well, T is a parameter, we have the extra degree of freedom, and then again, that gives us the motion, right? So we are going to put this orientation of the curve. So positive orientation is in the direction of increasing time. So let me write that in blood over here. Positive orientation is in the direction of the increasing parameter. So our parameter t can start at 0, which is 0 time, and then tick 1, 2, 3, 4. Now, as you draw the vectors, vectors are going to go one way or the other way, whichever way they go as progression 0 through 1 through 3 and 4 goes, that's the orientation of the line. Now, I am going to draw now those 2 circles, make sure that you guys understand. So, absolutely same situation. Let's say these are both circles that are radius 4. And the first circle is going to have parametric equations 4 cosine theta, comma 4 sine theta. And the orientation on that one is going to be counterclockwise. On the other circle, I will have 4 sine theta and 4 cosine theta, and the orientation there is going to be clockwise. So this particular parametrization gives us the same circle. The black line, which bounds the circle, right, is going to be identical for both of these parametrizations. However, it matters where I put sine and where I put cosine because it switches the orientation of the curve. And again, that is something that is going to be very important in chapter 14. So, how do I know that this is the orientation that we have? Well, that's very simple to check. Theta equals 0. What do I get for theta equals 0? Theta equals 0, cosine of 0 is 1, so I'm getting 4 on the x-axis, and sine of 0 is 0, so 4 times 0 is 0, I'm getting 4, 0. 4, 0 is this point here. Now let me increase theta from 0 to say pi over 2. Fine. Cosine of pi over 2 is 0, and sine of pi over 2 is 1, so that's 4. So I have 0, 4. That's this point. So when I use theta equals 0, I have this point. When I use pi over 2, I get that point. If I use pi, I will get this point. It doesn't take too much brain power to figure out that it's this type of motion. Because as the parameter theta starts at 0 to maybe pi over 6, pi over 4, pi over 3, pi over 2, to hit multiple values here, you will always have this kind of progression. Now, try to calculate the same thing on the other one. You will immediately see the clockwise orientation. Because when you start at 0, 4 sine of 0, that's 0. And then this is 1, so you get 0, 4. You start here, 0, 4. And then you say, okay, let me see pi over 2. Pi over 2 is going to give you 1, and over here is going to give you 0, so you get 4, 0. That's this one. So you see, you start here, the next point is this one, and then the next one is that one. So that's the orientation for this curve. That's the power of parametrization. It is going to give you more than just what your functions are. Right? It's going to give you this orientation. So we are going to have, right, we're going to have that. Now, helix. Helix is a spring. So when you look, now you all seen spring at least once in your lifetime. Maybe your pen exploded on you and you found a little spring. So that spring is what the helix is. I mean, helix is much more than that, but okay. So what do I have? If you look at the little spring from your pen, right, you put it straight up on the desk and you look from above, you are going to see that the domain is a circle. With radius r. If you look at the spring on a side, you will see the constant progression going up, like that. Sure, it's going to curve, right? But if you just, take the closest, like you cut the spring in half, right? And somehow magically suspend that half, right? Keeping the distances like that, this is what you would see. Right, you will not see the curvature that goes back to the other one. So now, if I am trying to write the equation, I have my spot for x, I have my spot for y, and I have my spot for z. Well, xy creates the domain, and that domain is a circle. So I better put r cosine theta, or t for time, r cosine t, comma, r sine t. That already took care of the circle in the domain, because domain is what you see on the floor, right? You shine the light on the spring, it will give you the circle shadow on the floor. And now z, well, this is connected to z. And what I see are series, well, in this case, no, I did draw a positive one. So I should have done this. There we go. So now we are going to call this one, let's say, t. It's a linear progression up, right? It could be 2t, right? It could be 7t, right? That depends on how steep, right, the spring is. So I have my domain here because that's the parametrization for a circle. And then this one is the one that is going to spiral up linearly. So all of the, call them levels, right, of a spring are going to be equidistant. right? Just like what I have over there. So they're equidistant as you move up. But you can put any other function here, and you can make this spring, like you put e to the t, the spring is going to start winding slowly, and then as soon as it hits 1, it's just going to go whee, right? Because it is really going to spiral up on the part above 1, because we know what exponential function does. Slow, 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 hits 1, and then it just takes off, right? Yes, and it's going to stay stretched, right? It's not going to have nice curvature anymore. It's just going to stay stretched. I can put t squared. I can put anything there, right? If I want to compress the spring into a pancake, right, and have no spiral, because it just smooshed it like this, I can put 0, I can put 1, and that would be a pancake on 1. It would just be a circle, right, because I smooshed everything in one ring. Right? Well, you can think of a ring, right? Lord of the Rings? Yeah, good. So you put that one on the z equals 1, and the equation for that would be this, 1, because it's lifted, right? 1 unit off. Remember that this is z equals 10, and the floor is z equals 0. So if something is 1 unit off, well, z equals to 1. Z equals to 1. You put it at the level 6, it's a 6 over there. And then they have all kinds of nice, like a slinky. I say slinky curve, right? You know the thing, when you play like this, I have one in my office. Yeah. Right? So I would never give a child this to play with because they don't know the equation for it, right? Like if they can tell me the equation for it, then sure, play. Stands on a shelf. You can look at it, but until you know the equation. Right. It's like, yeah, there it is. Right? Because it unlocks. It's you know, like achievement, you know? You unlock the achievement and then you get a prize. So yeah.
Working then.
So many kids, they go to my office and they go, gotta know the equation, sorry. Right? So that's that part.
So when they tilted onto when it was tilted onto the XY plane instead of the where it was going up and down, how you have it in your example, how does it change the equation? Because is T
like if it was this way?
How it was in that picture.
Oh, the picture that I removed, you want me to bring that back? Are you talking about this?
Yeah.
Okay, so observe that you have cosine and sine, which gives you the circle. Look at that one. Parametric equations
like
in terms of t.
Equation U.
Right?
One at the bottom right.
Exactly. You know what that means, right?
What?
I think it's time with a break, right? On space and stuff.
It's been long enough.
Well, yeah. I mean, it's not going to know this, then life is going to be tough, right? To communicate later on. It's like on two different planes, you know?
I like ET, so it's totally different language.
Well, so yeah, so you have some, so this is a polar representation, right? Because you have r as a function of theta. So it's a polar representation. That's actually called a cardioid. You have that. We are going to deal with that, actually, cardioid. So this one is good. More polar representation over here. But yeah, parametric one. I think the parametric one is the best.
Yeah.
Prettiest, yeah.
Right?
No, I
You're
think
looking at
was
this
nice.
and a parametric one. So that's that, right? and you say I,
Yeah.
you. Huh? Let them figure it out. You can do so many this course, you have no idea. Especially if anyone comes along and say, what do you know? What do you know? It shuts it down like immediately.
Just hashtag math is power. This is what we should add to that.
I know.
Hashtag math is power. This is, we should Instagram
Do I have it?
And hashtag.
Do I
This
have?
picture.
Oh no, it crushed. It's
Love
crushed.
it.
Oh. Yes.
Somebody's number on a napkin.
It's a bar napkin with the differential equations on it, given to me by the student.
What?
Yes, said I ruined their lives because they can't even have fun without doing DFQs. There's the proof right there. I also have a pizza box with differential equations in the office when someone handed in the homework. Yeah, it was minute to midnight, right? Have to do the homework. I gotta preserve this. It's getting crushed over here, so there you go.
What other interesting things do you have in there?
I have a student who wrote, was annoyed by the college, graduated, took all the classes, walked the thing, and they refused to give him diploma because he owed $10. Came up with integrals and sequences and series function and wrote that on a check. I have a picture, yeah. I have a picture of that check. And wrote on the memo line, thank for the knowledge.
Was the check accepted?
Yeah. They cashed the check. I guess they went to someone in the math department and said, what the hell is this? They said, it's 10. It's like, oh yeah, that's what he owes. So great. Boom. Sent him diploma, which was really interesting. And many other situations. Yeah. So, as you can see, parametric functions, very useful, right? Very useful. And I think that's it. Oh no, limit. So no, I am not going to go over the limit because the next section, 11.6, is calculus of vector-valued functions, and calculus consists of limits, derivatives, and integrals. So this one part, which is limits of I'm going to just merge with the rest of the 11.6. Now, guys, it will take me maybe about 18 seconds to teach next section, next class. So we are going to probably finish all of the material. Now, the last section is extremely long. We have 3 sections left. No, 4 sections left. 4 sections left. So we will probably be done with the material. We need to talk about the exam. So we'll probably be done with the material either Monday or Tuesday. Sorry, no Monday. No Monday class. It's a holiday. No Monday. Monday school is closed. So if you drive to the parking lot and see no one, please, the face palm, make sure you capture that on the video. So school is closed on Monday, but we might be done on Tuesday, or probably Tuesday we'll be done. Right? Tuesday we're done. We should talk about the exam either today, since we have time, or we can talk about the exam tomorrow.
We should wait for 28th.
Or actually, wait. We have 30 minutes. I can teach the 18-second section. Exactly. So
We're not waiting for
exactly. So I'm going to restart the stream for the next section.
It'll be an 18-second video.
Well, it's just